Suppose you have a photon, right? And here's the photon, and let's say this is the energy of the photon. It's got some energy. And then it interacts with a, I'm going to say, heavy nucleus. And you see why something like that is kind of needed. So it comes in. I mean, this is something that's observed in laboratory, so it is like magic. But of course, it's physics. A photon coming in of, let's say, high energy, it interacts with, let's just say, a heavy nucleus. And then this is before, like this is before. And then what you see afterwards is this. You see the heavy nucleus, and it's roughly at rest because it's heavy, it's got a lot of inertia. And then what you see is a particle that goes this way with a certain mass, and another particle that goes this way. And let's say we want to consider the creation of an electron. So if this is an electron, right? It's got some energy. How about I call it E, what did I call it? E minus? No. Only minus because an electron is a negatively charged particle, right? So that's the energy of the electron. I mean, I'm not saying that this is the vector that denotes the energy. Energy is a scalar quantity. I'm just saying the energy, maybe I should write it over here. Well, it doesn't matter. Electron. But what's also observed is another particle that has exactly the same mass as the electron. Exactly the same mass. But it's positively charged. It's got exactly the opposite charge. So it's a plus particle, and this is called an anti-electron. And let's say the energy of it is plus. Well, I mean, these energies are positive. It's just that this is the energy of the positive particle, and this anti-electron is called a positron. So this is the energy of the positron. Okay? So how about we use conservation of energy? I mean, this is what's observed experimentally. So what if we use conservation of energy? Conservation of energy. What's the total energy of it here? Let's say a heavy nucleus at rest. Okay. And the mass of the nucleus is m sub n, well, nucleus. So what's the energy of this photon? It's just the energy of the photon, right? Whatever that is, plus. What's the energy of the nucleus? It's at rest. So it's just the mass times the speed of light squared with no kinetic energy. So plus the mass of the nucleus, c squared. Now, what's the energy after the collision? And from conservation of energy, this energy has to be equal to this energy. So it would be the mass of the nucleus, which doesn't recoil much. It's actually there to conserve momentum. But we'll just say m nucleus times c squared at rest. It just recoils a little bit. And then we would have the energy of whatever this is. Well, it's the energy of the electron, which I call E minus, plus the energy of the positron. And notice that this cancels this. Essentially, the energy of the photon gets completely converted to material particles. So the energy of the photon it gets transformed into the energy of the electron. I mean, I guess if I write electron, I don't have to write the minus sign, plus the energy of the positron. Now, what is the energy of the electron? It would be the rest energy of the electron when it is at rest, plus the kinetic energy of the electron, whatever that is. And what is the energy of the positron? It will be the energy of it when it is at rest, and it has the same mass as the electron, plus the kinetic energy of the positron. And because these two masses are the same, I get twice the mass of the electron multiplied by c squared, plus, and then I get the kinetic energy of the electron, plus the kinetic energy of the positron. Technically speaking, which of these two particles do you think is going to have more kinetic energy? Can you argue and say it's this one? The who?
The proton?
The positron. Why? That's correct. That's the right answer. Why would it have, let's say, slightly more kinetic energy? So, this guy plays a role. The charge of a nucleus is positive. So what is it going to do to the positively charged particle? Push it away. And what is it going to do to the electron? Like, stay with me, don't go away. Right? So a little kick and a little pull. But nevertheless, the energy of the photon. And what about the energy of the photon? Can we use an expression for the energy of a photon? H times the frequency of the photon. So notice, how come, if I ask you, what is the minimum energy that the photon needs to have if it hopes to have all of its energy converted to the material particles of the electron and positron pair? It has to at least make their masses. The minimum energy is when the photon comes in, interacts with the heavy nucleus, and creates the electron and the anti-electron. And let's say the electron and the anti-electron are not moving. Okay? It's like, suppose the energy of the two particles created, suppose it's money. Suppose this is together $1,000. And then maybe this is, I don't know, 25,000, oh well, no, $250. And I don't know, maybe I'll make this one $300 for the sake of argument. Right? So for this process to occur, the energy of the photon has to be 1,550. Right? The less energy the photon has, the less kinetic energy the electron, the less money the electron and the positron are going to have. Right? But if I ask you, what is the minimum energy that the photon needs to have if it's going to make the electron and the anti-electron? Well, it's when it doesn't give them any kinetic energy, which is $1,000. And since the rest energy of an electron is 0.5 MeVs, so the minimum photon energy would have to be 0.511 MeVs times 2. So this is like 1 million electron volts. And that's in the electromagnetic range of the spectrum, from radio waves, microwaves, infrared, visible, UV, X-rays. These are gamma rays. So why is it that in this room we don't see electrons and anti-electrons being made in this room by the light? There are atoms in this room. There are oxygen, nitrogen, molecules, and so on. How come we don't see electrons and anti-electrons being made all the time?
Because the frequency isn't high enough.
Because the energy of the photons coming out of this light, for visible light, the photon energy is from like 1.5 to about 3 electron volts. You need 1 million electron volts to make electron-positron pairs. And what would happen if this photon hopes to make a proton-antiproton pair? Well, because a proton is 1,000 times, almost 2,000 times more massive than the electron, then the photon needs to have more energy to start with, to at least make the mass of the proton and antiproton. So usually the lighter particles, the lighter antimatter particles are the ones that are created first, because you usually ramp up the energy of these particle accelerators up more energy, and then new particles that are heavier begin to pop up, begin to be made. But right, so there's a formula over here that I don't memorize. I don't really memorize. What is the minimum energy? Right? It's something like that, right? So I just think of it. You have the photon coming in, and it has to at least make their masses. And what is the energy of this electron at rest? MC squared. What is the energy of the anti-electron at rest? MC squared. So 2 MC squared. That's the minimum energy. Any additional energy that the photon has is going to be endowed to the electron and anti-electron as kinetic energy. It'll be shared between them, right? this expression just says that, any extra energy will be shared between the electron and the anti-electron, the positron. And what I'll say next time is what happens if an electron meets an anti-electron. So the easiest case, imagine they're both at rest and they're near each other and one tells the other, "Ooh, you're negatively charged." "Yeah, and you're positively charged. I love you. Let's get together." Boom, they get together and they go out of existence. Completely out of existence. No more electron, no more positron. And instead what you get are 2 photons emitted. Now what do you need 2 and not 1? Conservation of momentum. If these 2 are at rest, if you go to the frame of reference when they are at rest, the total initial momentum is 0. If only one photon is emitted, that one has momentum. And so therefore the final momentum wouldn't be equal to the initial momentum, so momentum is not conserved. But in all of these interactions, momentum is always observed to be conserved. So therefore, and they always see 2 photons going in opposite directions with the same energy. Because if they have the same energy, they'll have the same momentum, and then this momentum will cancel that. So essentially, these 2 have the same mass. And because these 2 photons have to add up to 0, they have to have the same frequency and the same wavelength and opposite momenta. So it's like the energy of this positron went to make this photon, and the energy of this electron went to make that photon. So mc squared equals hf. I just took this from another book where they call frequency nu, the Greek letter nu. Instead of that v is not, that stands for frequency. And so the energy of each photon, therefore, is just conservation of energy, and using conservation of momentum, the energy of each photon is just the energy of each of the particles. So you could have 2 material particles, one matter, the other one antimatter. They meet, they completely annihilate each other, they go out of existence, and boom, you get these gamma rays. And because the mass of an electron, which is so light, right, it's just, the rest energy is 0.5 million electron volts, right? Then we got a photon with an energy of 0.511 million electron volts. It's in the gamma rays. So electron-positron pairs produce gamma rays when they annihilate. Okay. So this expressions over here, I don't memorize this expression. I don't memorize this other expression over here. If I think of the process and I just, I know what the momentum of a photon is, what the energy of a photon is, I can very quickly figure out the results. So, that's, and then there's something else over here. But that'll be for another day and another time. So next Tuesday, you have a quiz on chapter 35, 36, right? I haven't written it yet. And then next Thursday, you have your second exam on chapters 33 to 36. So today, we're going to do a lab on single slits. Okay? I'll explain it to you. It's relatively short. But I'll tell you about it when we get there. If you need, should we meet at 3:30 or we should meet at 3:20? I'll open the lab anyway if you want to hang out in there. Okay. Have a good weekend. Well, I'll see you in
yeah.
sorry. So, I'll see you later.